Okay. Um, so today I'm going to be talking about, I'll give you guys a little intro to symbolic execution, and I'm going to be using Angr as a tool to kind of introduce that to you. A little bit about who I am. My name's JC. I like climbing, card games, reverse engineering, binary analysis in general. And just like a disclaimer, I'm not an expert on symbolic execution or Angr for that matter, but I kind of just wanted to share what I do know and kind of like show you some examples of how to use Angr. So like, what is symbolic execution? It's a method for basically taking a binary, emulating all the code paths that binary can take, and then telling you what inputs to this program are going to cause different paths to be taken. And this is really useful for, it has like a lot of uses in testing, reverse engineering, and vulnerability research. Kind of an example of like what that kind of looks like. If you have a simple program like this, what's going to happen is that when you're symbolically executing it, it's going to try to emulate this program, and every time there's any value that it doesn't know, it's undetermined at runtime, it's going to replace it with a symbolic variable. So in this like simple code snippet, like that would be argv1, right? That's going to be like the argument for the program. You're not running the program with an argument, you're just dry running it, and that's going to end up being a symbolic variable. So what happens after that is that you can see that there's a if statement there. What's going to happen at that point is that when you're symbolic executing, and this depends on if you're doing an online symbolic execution or offline, the difference being that like in online symbolic execution, you're going to execute every path at the same time. So like in an online symbolic execution, what would happen is that two states would branch off from this, and there would be a different path constraint on each one of those states. So one state would have the path constraint of if the password equals number 10, then that's one path that's taken. The other state would have a path constraint that says if password is anything that's not 10, then this path will be taken. So that's kind of like a simple example of how this works. Just some like quick definitions. The difference between concrete execution and symbolic execution. Concrete execution is just like what we always do. It just means we're running with concrete values. Nothing is left undetermined. Basically running it on like your own on your OS, on your hardware. Symbolic execution means we're going to emulate it, and every time we come across something that is unknown, we're going to replace it with a symbolic variable and kind of just continue execution. And anytime something happens to that variable, we kind of just say, all right, X, and then like whatever operations happen to that variable, right? And then at the end of the day, you're going to end up with kind of like an equation you can solve for whatever the input needs to be to get to that path. I kind of talked about online versus online symbolic execution. There's static symbolic execution and dynamic symbolic execution. Dynamic symbolic execution just means that you're symbolically executing the program, and you're also like concretely running it, and that kind of like that works to like, because a lot of the time an issue with symbolic execution is that it's not you have to emulate the whole environment, right? So like if we're on like Windows, we have to emulate how like dynamic loading works in Windows, right? And that's a lot of work. That's a lot of code to emulate. So kind of dynamic symbolic execution is there. It's kind of like an easy route out. Let's like execute what we can concretely, and then kind of transfer that over to symbolic execution, and then let it take charge from there. Bit vectors is just like, that's what we're going to be working on, right? When we're executing a program and emulating it, we're going to take the assembly instructions. We're going to turn them into an intermediate representation. And then with this intermediate representation, we're going to try to represent that using bit vectors. The reason, this isn't necessarily the path you have to take, but Angr uses bit vectors, and the reason we use bit vectors is because Z3, which is the constraint solver that works under the hood in Angr, uses bit vectors, or can use bit vectors. A basic block is just like a block of code. So like, to show you what that looks like, that's basically just that's like this block right here, right? So like these two would be two separate blocks of code, right? And any box here, that's a block. And basically what that means is just like it's a solid bit of code that runs. And like the entrance is like, you know, it has to be branched into that, or like the exit is like it branches into something else. And then constraints are basically just constraints on a state, right? Just like to get to this path, it must meet these constraints. So like constraints and constraint solvers, like it seems like a super simple thing, but apparently it's not. Apparently like there's a lot of math involved. So basically we have in the field of like math, like really advanced like algebra, like abstract algebra math, like we have something called like constraint solvers, right? And we have different ways to do this. There's SMT solvers and SAT solvers. The difference between those two specifically is I'm not gonna explain the acronyms because I can't even like pronounce the words in the acronym. But basically, an SMT solver is gonna work on a like field of like integers. That's gonna work on integers, and like you can do like integer, like you could do something like x has to be greater than 10. An SAT solver is just like, it just uses Boolean values. So you can say something like x has to equal this number or cannot equal this number, right? So that's basically just about like a bunch of hot fire flames math. Don't worry too much about that. Just trying to give you like a background of how this all works. So kind of just like a pros and cons. Pros, it's gonna simplify like certain problems that would take much more time manually. Ideally, like you don't need to concretely run the program, so that means that you don't have to be on like, if you want to like analyze like a Linux binary, you don't have to be on Linux. You can do that on Windows or Mac OS. And it can be used to determine like the reachability of vulnerable code. Like if you know like a code snippet is vulnerable, like how do I get there? You can kind of find out and figure out what the input is. The kind of cons is like it requires a decent understanding of the problem being addressed. And part of that is because it's not very scalable. So ideally, you want to only execute the instructions you care about, and you want to put as much constraints on that as possible, because you don't want too many symbolic variables. You don't want symbolic variables that like if you don't constrain like the kind of problem you're facing, then you're going to end up with path explosion, and you're going to end up with like a state that can't be constrained. It's not satisfiable, right? It's like we don't know how we could get here because we don't know enough about the problem we're dealing with. And there's also a lack of environment support, like I mentioned earlier. Like you have to, like for example, Angr, which I'm going to be showing you guys right now, is it has like pretty much no macOS support like whatsoever. But you can still solve problems as long as they're simple enough. So I'm going to show you some like CTF problems in a second here, and how you can. I'll show you one that's a macOS CTF problem, and I'll show you that you can solve it even though Angr doesn't have much support for macOS. So like, what is Angr? What the fuck is that? It's built on top of it's like built on top of a lot of code, involves a lot of different aspects. CLE stands for CLE loads everything. I know that's like recursive and weird, but that's what it stands for. It doesn't load everything. It unfortunately doesn't work on MacOS, but this is basically the binary loader that's going to work on the back end of Angr. Angr also uses PyVex to basically emulate the instructions. Vex is an IR used by Valgrind. And the Angr developers felt that PyVex and the Vex IR specifically was best suited for symbolic execution. ClaraPy is basically just going to take the IR that's spit out by PyVex and represent that in bit vectors. And bit vectors is what Z3 deals with. So Z3 is an SMT solver, and that's basically the solver at the back end of Angr. That's going to like, once we figure out a path, we're going to take all the path constraints, give it to Z3, and Z3 is going to come up with a solution for us. Angr is a binary analysis like suite. It doesn't just do symbolic execution, so it can also do things like control flow graph generation. It has a ROP gadget finder. It has a GUI called Angr Management. So it's pretty nice. I should say it was written by Shellfish, which is a CTF team full of like PhD students from UCSB. I believe Angr is developed out of UCSB. And it was used in their mechanical fish project, which is basically what they used to compete in something called the DARPA Cyber Grand Challenge. And it's basically, that year the challenge was basically, can you come up with a system that can automatically detect vulnerabilities in programs and then automatically generate exploits for that program? And they actually used Angr to do that, and I believe they won second place and like $500,000, I believe. I may be wrong, but yeah. So kind of like how Angr works, I won't spend too much time on this, but the basic idea is that like it's loaded by CLE. It's then like, it takes the assembly instructions and they're lifted into a Vex IR. That's what PyVex does. And then You have a sim engine and SimOS. Sim engine is there to simulate the vex IR instructions and kind of come up with change them into bit vectors. That's why Clarify is there. And SimOS is going to like simulate the environment. So if you're in Windows or Linux, it'll simulate dynamic loading on those platforms. And also other things like library functions like libc and stuff like that. All of those have to be simulated. Okay. So like, now we're just going to go over like a few CTF problems and kind of see how to solve them using Angr. I'm going to be using Binary Ninja just because it gives me a Python console. Nick mentioned that I was going to, what's that? Okay. Nick mentioned that that I was going to like show you guys the Binary Ninja plugin. That's true. I'm not going to release the source code because it's not finished. It needs a lot of work, and it only works in a few cases right now. But I'll kind of show you what that looks like at some point. As you can see, the Python console is broken. Give me a second. Okay, so we're just going to import some libraries we're going to want. So Angr and Clarify. Clarify is going to be used so I can make like symbolic expressions. This problem is super easy, right? So we want to take a look at the problem first. This is it's just a crack me and it's asking for a password from standard in, and there's 2 paths it can take, right? So Angr can solve this problem like super easily, right? So we're going to create an Angr project. Can you guys see that? Should I make it bigger? So I'm using bv.file.file name. This is just like the name of this file, right? I'm just using the Binary Ninja API to like kind of help me out there. Then we're going to create a state. So this is basically going to be like our starting state, and we can there's different functions we can use in Angr. I'm going to use project p, which is our project object.factory. And we're going to do a full init state. What this means is that it's going to basically start us off over here in start, in like the libc start function, and it's going to emulate all the, like libc start main and all that initialization stuff. Yeah, so we'll do something simple like that. And our next job is to create a simulation manager that's also in factory. And we just got to give that an initial state to work with, right? This is like the first state where it's going to start at. And then it's as simple as just saying, telling our simulation manager, I want you to explore. We'll see what instruction this message is at. And say, I want you to find this address. I want you to show me a path that takes me to this address. And it gets it. These warning messages are just telling you, like, okay, I had to fill this register with this many unconstrained bytes. I had to fill memory with this many unconstrained bytes. At the end of the day, it doesn't matter because those specific values don't really matter too much as far as the execution of the program goes. So at this point, we can take that found state. It gives you a list of the found states. So each of those, what you're looking at there are like Angr stashes. So there's one active stash and one found stash. And each stash is basically just a list of states. So we're going to take the first, the only found state there is. And since this particular CTF challenge took its input from standard in, what we're just going to say is for this found state, you access the POSIX object, and basically you can dump, standard in by using 0, standard out by using 1. So like if we did standard out, it would show us like the prompt. If we do standard in, it shows the flag for this problem. I believe this one's crack me 2. So if we go and try this out, crack me 2. And we gave it that password that Angr gave us. Then it'll say password okay, right? That's kind of small, but yeah. Kind of show you a more complicated example. And I guess real quick, I'll try using my plugin. I don't think it's gonna work, but I'll try using my plugin. Basically, I can init a state here, I can say no arguments because this is taken in from standard in. It's going to highlight that block that it's executing at. We'll go here and say, all right, find this instruction. It'll say that it found that instruction. If we go to the log, we'll see that it gives us our solution right there. It only works for this case. So it's like, it's not worth clapping for, but that's pretty cool. So now I'll give you an example of using like something more complicated where there's like a lot more checks and there's a lot more caveats you want to deal with. Because this works best when you like give it like a very, when you specify as many constraints as possible, that's when this works best. So what I'm going to do is, last time I did a full init state, but this time we're going to try actually, this is really buggy. Okay, all right, that's fine, that's fine. So this time we're gonna make another project using this binary. All right, so this is another CTF challenge called prod key. And I'm not going to start at main this time just because I feel like I want to get straight to the point. We know that this verify key is going to verify our key, and we know that we want to get to this block where it opens the flag.txt file and prints it. So I just want to start at this instruction. The reason I'm going to choose this instruction is because this is where it's loading our key off the stack, and it's putting it in RDI so verify key can work with it. And basically, we just want to execute that and basically figure out how to get to this address. So what we'll do is we'll start right here. If you press here and binary ninja, I believe it gives you the address. Yeah, okay. So we'll create our state. Factory. We'll do an entry state, and we'll specify our adder as here, which is it's just an instruction I'm highlighting. That's just me using the binary ninja API again. And I believe this takes it in through standard in, so that's all we'll do. And then we'll create another simulation. Oh, actually, we have to set the state up first. So right now it has no idea what's on the stack because I didn't do any like initialization or anything. So just to set that up really quickly, we can do a state memory store. We can use the state object to also like access the value of RBP at that point. Mine is set by OX90. Yeah, OX90. And that's basically the address where we're storing something, and we want to store symbolic vector there. So actually, my bad. Let me make that first. So this is me just creating a symbolic vector. I'm going to give it basically just a symbol name, so I'll be like arg, and tell it how many bits is the symbolic vector. For this specific case, I have no idea, so I'm just going to say something like 50 should be fine, right? 50 bytes, hopefully that's enough to hold the flag. It doesn't really matter if you're making a symbolic expression that has a larger size than whatever your flag's going to be. So we're going to go and make that simulation manager now. Or actually, store that real quick. Store state, so it's 90. And we're going to put our symbolic vector there. And then we can make a simulation manager using that. I don't know how to spell manager. And we basically want it to get to this point. So we'll take this. We'll say simgr.explore, find equals. So this may be very worrying, but it's just going through all the possible states. And unfortunately, in this particular example, I'm not sure why I didn't check beforehand. But basically, what's happening right now is that it's going through a bunch of paths that are unsatisfiable, right? They're unconstrained, and the reason it's basically dumping those states. So once what's happening, if you look at the warning messages, it says something about exit state has over 256 possible solutions. What would happen typically with Angr is it's going to be like, all right, let's make a different state for each of these possible paths, and then just keep going with that, right? But it's not going to make 256 copies of that one state and keep executing, right? That's unreasonable. So it just dumps those states and moves on and tries other paths. Anyway, let's look at our found state. What we're going to do, since we use a symbolic variable this time, is we're going to take our found state, we're going to use the solver, and we're going to eval for that symbolic variable. And this is basically just grabbing the symbolic variable, taking the constraints, passing the constraints to the Z3 constraint solver, and then Z3 comes back with a solution. We're going to the answer is given back to Angr as a bit vector, so we want to cast that to bytes. So this is a working key, believe it or not. I didn't put you can add constraints to this to basically make it so it's actually something printable. It's not like a bunch of bytes that aren't printable. But I'm pretty positive if we give this to the program. I'm going to have to use Python, unfortunately. Is that working right? Yeah, okay. Yeah, so we can see that it does actually solve the problem, and we would get our flag if we were using this on like the actual server where the CTF challenge originally lived. So yeah. Depending on if you guys are interested, I'm gonna ask you to raise hands because it's almost 4 o'clock, I think. There's a Mac OS example here, and I can do a lot and show you more of like Angr's capabilities and show you how we can even solve this Mac OS example despite the fact that Angr doesn't load it, doesn't do any relocations, and doesn't implement any kind of dynamic loading. If you want to see that, raise your hand. No one has risen their hands, except, all right, no? Okay, so we'll just move on. So like, yeah, just there's different state generators you can use. As I was showing you when I was generating the states, you can do a full init state, which is basically like just run the program. Entry state, which is like start the program at the entry point for that binary. Blank state is just a blank state, just like tell me like where to start, and then like I won't do anything else, just a blank state. And a call state is basically give me an address for a function, and I'll call that function. Some options you can use when you're creating a state that are useful, not useful. You can use unicorn, which is unicorn is going to concretely like execute. So like anytime, it basically implements dynamic symbolic execution in Angr. So anytime we're going to use unicorn to emulate instructions instead of using the vex IR. You can do zero fill unconstrained memory registers. So that's just basically if there's anything in memory or in registers that's unconstrained, we'll just fill it with zeros. Lazy solves, that's basically the feature I was showing you. It's on by default. So basically, like if we come across a state that has like 256 possible successors, just dump that path. Don't continue down that path. You can use bypass unsupported syscall. That's basically gonna like, once it comes across a syscall that hasn't been like implemented in Angr, then it's just gonna bypass that. You can use downsize Z3 if you're having like issues with memory. That's basically gonna make it so Z3 doesn't use as much RAM as it typically does. And use system times is an option that's helpful for when you're exploiting a binary that uses something like the system time to create a random number or something like that. You can use system times will make it so Angr actually grabs the system time from your OS and uses that. Ways to make Angr better, we can make like sim procedures. So like sim procedures are basically like basically they'll hook like library calls like get s, print f, stuff like that, and sim procedures are just like telling, all right, what happens to an Angr state when this library call is made, and those are important for like emulating those library calls. You can also write like your own analysis. There's a bunch of classes in Angr that you can subclass. You can subclass an exploration technique, and this allows you to basically, at every step that Angr is executing, you can basically like hook in there and be like, I don't know, like print this or print that. Adding support for different architectures and documentation. Even though the documentation for Angr is really good, if you're like interested, you can go look at it there. There's a lot of great documentation at docs.angr.io, and there's great API documentation. Just as a note, I didn't mention it. I didn't do any demo of it here, but you can also use Angr, like I mentioned. You can use it to like find vulnerabilities. Kind of what that looks like is like you would tell Angr to basically just step through a program, right? And if at any point what's it called? The instruction pointer. If at any point the instruction pointer, this is like a simple example of like finding vulnerabilities. If at any point the instruction pointer becomes symbolic, and that symbolic buffer is under user control, you can detect that using Angr, and basically you can use it to assist in like basically automatically generating exploits for CTF challenges or like actual applications. So that's all here. A bunch of resources I used to learn about Angr. And any questions? Okay.